quadratic functions. The Q is for crazy. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are putting a 2 above an x and seeing what happens. Quadratics are the next highest order function that we're going to be looking at, and it really sets the standard for how we deal with polynomials and functions in general. But what are quadratics? Quadratics are second-degree polynomials, which means that their highest power is 2. In standard form, they look like this. f of x is equal to ax squared plus bx plus c. A, b, and c are things called coefficients, which are multiplicative factors on the end of the x terms. A is called our leading coefficient because it's the first one attached to the highest power of x, x squared. Bx is called our linear term because it's proportional to x, much like a linear function is. And finally, c is our constant term because it's just a number, it's a constant. But I can write quadratic functions in different ways, like this vertex form here, which is equal to f of x is equal to a times x minus h squared plus k. A again is our leading coefficient. H represents our horizontal shift of the vertex, and k represents the vertical shift of the vertex. And in fact, h and k give the coordinate point of the vertex of the parabola. More on the vertex in a moment. Finally, I can write quadratics in a factored form, which looks like this. f of x is equal to a times x minus m times x minus n. This form gives us our x-intercepts, which would be m and n of the function. Now, not all quadratics can be written in this form with real numbers. In complex numbers, they can be, but since we're sticking with real numbers for now, it's good to know that not all quadratics can be factored this way. I can convert between these 3 ways of writing quadratic functions using some algebra. For instance, to get from standard form to vertex form, all I need to do is something called completing the square. To get from vertex form to standard form, I factor the stuff in parentheses and combine like terms. To get from standard form to factored form, I factor. To get from factored form to standard form, I FOIL the factored form. Why even have 3 ways of writing these things? Well, each one gives us specific information about the function, which can be very useful. We've already talked about how the factored form gives us our x-intercepts, and the vertex form gives us our vertex point. Standard form also gives us useful information. Those a, b, and c coefficients can be used in the quadratic formula to find the x-intercepts. And we can find the vertex by using the equation x of the vertex is equal to negative b over 2a. Quadratic functions always form something called a parabola, which is a curve that forms a vertex at one point and then flies off infinitely in both directions. All parabolas have some key features. They have that vertex at h, k, and all parabolas are symmetric along the line x is equal to h. If h is equal to 0, then the parabola is symmetric across the y-axis, which then we can say that the function is even. The vertex is an extrema of the function, which means that it either forms a maximum or a minimum on the graph. The domain of these functions is easy. It's just all real numbers. We can put in any x value, positive, negative, 0, whatever we want, into these functions. The range is a little bit different. It is dependent upon both the leading coefficient, a, and the vertex. If a is positive, then the function is something called concave up, and the vertex is a minimum. If a is negative, then the parabola is concave down and has a maximum at the vertex. In the first case, where a is positive, the range of the function is from k to positive infinity. In the second case, where a is negative, then the range is from negative infinity to k. The end behavior is similarly defined. For instance, if a is positive, we can see that both as x approaches negative infinity and as x approaches positive infinity, y is always going to approach positive infinity. When a is negative, then as x approaches negative infinity and as x approaches positive infinity, y always approaches negative infinity. Okay, what about the x-intercepts? As we saw before, if we are able to put this into factored form, then the zeros just fall right out of that form. They are m and n. We can also use the quadratic formula to find our zeros. Not all quadratic functions have zeros. Some have 2 zeros, some have 1 0, and some have 0 zeros. In the case of only 1 0, that zero is said to be degenerate. It repeats within the function. So I might have a function of the form f of x is equal to a times x minus m squared. If that's the case, then that 0, m, repeats twice, and therefore the function bounces off the x-axis at that point m, and it only has one x-intercept. Okay, so what about transformations? Well, the parent function of these quadratics is f of x is equal to x squared. If I want to move that to the left or right, I can add an h term to the x squared part of the function. So this becomes x minus h squared. If I now want to stretch or squish the function or dilate it, I can multiply it by a factor of a. So I get a times x minus h squared. If I then want to translate it up or down, I need to add a term k to the end of the function, so that I get f of x is equal to a times x minus h squared plus k. So our transformations are entirely equivalent to our vertex form of the function. Looking at a for a second, if the absolute value of a is greater than 1, that squishes the function closer and closer to the y-axis. I like to think that it is getting to infinity that much more quickly. If the absolute value of a is less than 1, then it stretches it across the x-axis, and it gets to infinity that much more slowly. If a is negative, that flips the function across the x-axis or reflects the function vertically. Bonus fact, did you know that all parabolas are similar? That means I can scale any parabola using some factor and fit it into any other parabola, just like a circle. All circles are similar, so are all parabolas. In the next video, we're going to be tackling an example, but for now, why don't you try it out yourself? Write the function for the parabola that has a vertex at 2, 3 and passes through the point 5, negative 24. Go ahead and also find the x-intercepts of that function. Try it out, thanks so much for watching, and I'll see you in the solution.